A very good evening to one and all. Myself, Sapna Gangrade, Assistant Professor, EC Department, welcomes you all to attend this grand 2-week ATAL AICTE-sponsored FDP, organized by our department and is scheduled from 19th September to 30th September. I'm extremely overwhelmed to get this opportunity to welcome our chief guest and keynote speaker, Shri V. Gopala Krishna Garu, Professor Satish Dhawan, scientist at National Remote Sensing Center. I feel proud to be a part of such an organization where we as a faculty members are getting opportunity to gain knowledge from such dignitaries. Now, on behalf of EC department, I would like to welcome our beloved Chairman Sir, Mr. C.A. Basha Mohiddin Garu, to join the session. Now, on behalf of EC department, I would like to welcome our Vice Chairman Sir, Mr. Syed Tausif Ahmed Garu, to join the session. Now, I would like to welcome our respected Principal Sir, Dr. C.V. Narasimhulu Garu, the coordinator of this ATAL AICTE-sponsored 2-week FDP. It is his guidance, support, and motivation which has helped us to make this FDP a success. Next, I would like to welcome our EC HOD, Dr. Shaik Muhammad Rasool, and all our dear participants from various states and countries. Before we proceed with the session, I would like to highlight some details of our college. Lord's Institute of Engineering and Technology, Hyderabad, was established in the year 2003 with the only motive of providing quality technical education. We have so far been successful since last 19 years to achieve our targets. We, as Lord's Institute of Engineering and Technology, has excellent infrastructure, facilities with modern laboratories supported by highly competent faculty members. We provide undergraduate programs in engineering like electronics and communication engineering, electrical and electronics engineering, computer science engineering with AI/ML, computer science engineering with data science, information of technology, mechanical engineering, and civil engineering with total intake of 1,080 students. Out of these courses, ECE, CSE, EEE, and ME are NBA accredited. Also, our college has been accredited by NAC with A grade. The college is confirmed autonomous by UGC since academic year 2021-22. We as an academician are honored and feel proud to be a part of such an institution. Now, proceeding with the session, I would like to request our HOD EC to say a few words about the department. Thank you.
Good evening to one and all. I welcome all the dignitaries who are joined the sessions.
Yes.
I would like to tell about my department. I am Dr. Shaik Muhammad Rasool, Head of the Department of Electronics and Communication Engineering. The Department of Electronics and Communication Engineering was started in 2003 with an intake of 120 students. Right from its inception, it is continuously striving to impact quality education and promoting competitive spirit among students for academic excellence. The department has well-equipped laboratories, good infrastructure, highly qualified and experienced faculty, a good number of research papers and published by the faculty in national and international conferences, proceedings, journals. The department has signed MOUs with various organizations to provide real-time training to the students. The department was sanctioned FDP under AQIS by AICTE and was successfully executed. The department has received patents in the field of image processing and microwave engineering. This is the brief of Department of Electronics of LIT Hyderabad. So with this, I welcome all the participants who joined here, who registered through ATAL FDP. I hope everyone will enjoy with all the online and offline sessions. Thank you.
Now, I would request our Principal Sir, Dr. C.V. Narasimhulu Garu, coordinator of this FDP, to address the gathering.
Thank you, Madam. Honorable Chief Guest and the keynote speaker for this AICTE sponsored 2-week ATAL FDP on recent trends in signal and image processing with hands-on training using MATLAB for 19 to 30 September 2020. And our Vice Chairman, Syed Tawseef Ahmad sir, Head of the Department, Rasool, and other deans, directors of the college, and my dear participants. At the outset, I would like to congratulate all the participants for applying for our FDP, and I thank all your managements, principals, heads for allowing you to enjoy and gain some practical experiential knowledge through this FDP throughout these 2 weeks. So the ATAL, ATAL, ATAL means AICTE Training and Learning. So ATAL, the last 4 years back, AICTE has started this program. Successfully they are running. Some hundreds of FDPs are being conducted in the emerging areas. So I also thank the AICTE authorities for sanctioning FDP for our college. This year, they have sanctioned only 6% of applied proposals. So we are very happy, and once again, thank you. Thanks to AICTE. So here we have chosen in the EC department, signal processing is one of the emerging areas. Hence, we applied this proposal on the title of recent trends in signal and image processing with the hands-on training using MATLAB. So in this FDP, you will be covered mathematical tools for continuous and discrete time systems and sampling techniques, spectral estimations, IIR filter and FIR filter design and realization. And you will be also gaining knowledge on multi-rate signal processing and filter bank theory, and excellent knowledge on time frequency analysis, image and speech enhancement, segmentation and compression techniques, morphological image processing and pattern recognition, and signal processing for 5G, signal processing for IoT, image processing for medical images, remote sensing, satellite image processing, and some statistical methods for machine learning and machine learning in image and speech processing. These are the broad topics to be covered in this FDP, and we expect from the participants after completion of this FDP, you will have in-depth knowledge and hands-on experience in signal and image processing concepts and tools. You will develop research and innovative orientation. You will be able to apply signal and image processing algorithms in various applications. You will be also develop a logical understanding and a comprehensive view of the applications of various signal and image processing techniques. You will be able to solve industry problems using practical approaches, including conventional to latest applications and will build substantial potential of problem handling. And you will have an enhanced pedagogical skills too. So you will be teaching very effectively signal processing, image processing, signals and systems, these kind of basic courses in your teaching career. So here we have invited the excellent, eminent, experienced resource persons from various fields and institutions, which includes today's chief guest, Sri B. Gopal Krishna Garu, Professor Satish Dhawan, scientist. He is NRSC ISRO. And tomorrow we have a resource person, Professor B. Krishna Mohan from IIT Bombay. On Wednesday, Dr. C. Raghavendra Rao, Professor, Central University, Hyderabad. On Thursday, Dr. P.K. Thiruvikram, Professor, BITS Pilani, Hyderabad campus. On 5th day, Dr. Anil Kumar Uppala, Associate Professor, IIIT Hyderabad. On 6th day, we have two resource persons. One is Dr. S. Venkatraman, Group Director, ADRIN, Advanced Data Research Institution, Hyderabad. And Dr. L. Nirmala Devi, Head of Usmania University EC Department. And in offline session also we have, I myself may take one session concept of orthogonality. And we have Professor S. Bhujangarao, former AGM ECL Hyderabad. And Dr. L. Koteshwar Rao, Principal KL University Hyderabad. Dr. J.V.R. Ravindra, Principal Vardhaman College of Engineering. And Dr. S.P.V. Subbarao, HOD ECE Srinidhi Institute of Engineering and Technology. And Dr. Prabhakar Rao from BITS Pilani Hyderabad campus. And Dr. J. Ravikumar, Associate Professor, Department of ECE, NIT Warangal. In addition to these, our local faculty members, Dr. Srinivas Reddy and Tausif Sumer and Mr. Mahammad Imaduddin, and several other people will join here as resource persons to guide you, to explain you, to train you in various aspects of signal and image processing, both theory and practicals. And as per ATAL FDP guidelines, we have they have different schemes. Okay, only in online FDP and hybrid, blended. So we have proposed for the blended. So here you will be having first 1 week in online from 7 to 9:30 p.m., 7 p.m. to 9:30 p.m. There is two slots, 7 to 7:50 p.m. and 10 minutes gap. Then 8 to 8:50 p.m., 10 minutes gap, and a half an hour interactive session would be there. And next week only physical sessions only there in the college, okay, from 9:30 to 4:30. Okay, it is for 5 days, 33 hours. We train you practically. Some tutorial sessions would be there. And as per this ATAL FDP, you will be assessed for 100%. You will be getting the certificate once you score 70% marks, and if you score more than 90%, you will be given distinction certificate. The criteria for the score is attendance will be taken for 10%, where you minimum required attendance is 80%. If you maintain 80% attendance, it will be considered as a 10% for your evaluation. And two assessments, one after each week. It will be calculated for 20% assessment. The questions, the test may be the combination of multiple choice questions and short answer types and reasoning based. And third is, we form some groups, 4 to 5 members as a one group we form. Each group will be given one article. So you have to prepare the summary, 2-page summary you have to prepare. So based on this summary preparation, you will be given 30% marks. Then teaching practice is 15%. And a report and outcome on industrial visit, either industrial visit or smart classroom training we are arranging in the college. It is given 10% weightage. Then finally, reflection journal he is given 15% weightage. So you used to write a report on this and will be submitted to the reflection journal. So overall, all these criteria, 10%, 20%, 30%, 15, 10, and 15. If you score minimum 70% marks, you will be given certificate. If you score more than 90%, you will be given distinction. So this is the criteria. So I request all the members, please attend regularly sessions. And we have received a request from several members. Sir, we are from distance, we may not be able to attend some classes. Okay, 80% is required. Okay, 1 or 2 sessions we may miss, there is no problem. And here the statistics is 50 members are approved for this FDP. Okay, in this 50 members, 17 members are from Telangana state, 16 members are from Tamil Nadu, 2 members from Andhra Pradesh, 2 members from Madhya Pradesh, 2 from Gujarat, 6 members are from Maharashtra, and 2 members are from Karnataka, and 2 members are from other states. This is the statistics of the members attended. So I really thank all the members for showing interest, okay, in applying for our FDP. And every day we post this attendance in the ATAL portal. So please join every day by 7 o'clock, and all sessions are recorded, and all the recorded sessions also should be submitted to ATAL portal. So with these few words, I thank our management for extending their support and providing necessary infrastructure in making this FDP a grand success. I also thank Professor Gopalakrishna Garu for accepting our invitation as and when I asked him. Okay, he is a nice person. He also gave a talk when I was in Gitanjali. Okay, so I really thank you, sir. Okay, I thank you, each one of you. Thank you.
Thank you, sir. Now I would like to request our Vice Chairman, sir, Mr. Syed Tausif Ahmed Garu, to address the gathering.
A very good evening to all the members who have joined us online for this inaugural session on ATAL AICTE sponsored 2-week faculty development program based on recent trends in signal and image processing. I think it's a very wonderful initiative that AICTE has started, wherein we've got our faculty members from all across the country who are constantly upskilling themselves, upgrading themselves. That is the need of the hour, basically, wherein you all have to constantly upgrade. If you see, we are all living in this globalized, technologically progressive world where everything keeps changing with every passing year. So it's a fantastic initiative by AICTE, and we thank them for selecting our institution for conducting this online and offline AICTE FDP program. And I think we've got a very good list of speakers. We thank Mr. Gopalakrishna sir for graciously accepting our invitation to be the keynote speaker. At the same time, we've got people coming in from IIT Bombay. We've got people coming from University of Hyderabad. Interestingly, Mr. P.K. Thiruvikraman, we used to call him PKT when I was on campus at BITS Pilani during my undergraduate studies. Professor PKT was very famous as a good teacher. He was a very friendly teacher and a very understanding teacher for us. And I'm very happy that he is part of the FDP program. And when I just saw the list, it made me feel very happy. And I invite all of you, those who are attending the FDP and who are conducting this FDP, to come to our campus, see what we have on offer, see the facilities that we have on offer, tell us how to improve ourselves, tell us how better we can improve the quality of education on campus. You are more than welcome. In fact, during the offline FDP program, I look forward to interacting with you when you're on campus, if the FDP is happening on campus, and graciously hosting you people. And all the very best for the organizations and for the organizers. Firstly, congratulations for getting selected. Like the principal was saying that only 6% of the applications have been selected this year. I think it's a something worth appreciating, that we've got this FDP. We've got the sanction for this FDP, and congratulations to the organizers and all the very best. And we hope to conduct many more such FDP programs in the future. Thank you.
Thank you, sir. As I have already mentioned that I'm extremely overwhelmed to welcome our chief guest and keynote speaker, Shri B. Gopalakrishna Garu. So before I hand over the session to him, I would like to present few words for our dignitary of the day. Our guest of honor, Shri B. Gopalakrishna, has received the MSc Tech Electronics degree from Andhra University, Visakhapatnam, India in 1981, and the MTech degree in Electronics from the Indian Institute of Technology, Kharagpur in 1984, with a specialization in satellite communications and remote sensing. He joined the Space Applications Center, Indian Space Research Organization, Ahmedabad in 1984. Since then, he had been involved and significantly contributed in the satellite data processing, image processing, and data analysis for IRS 1A by 1B, IRS 1C by 1D, TES, Cartosat 1, Cartosat 2 series, Chandrayaan 1 by 2, Cartosat 3, Astrosat, SCATSat 1, and Rasool Sat 2A. His core contribution include in-flight calibration, photogrammetric model development, satellite data processing, software development, data compression analysis, planetary data system development, and data simulation. He had many responsibilities at Space Application Center, from division head to group director of satellite photogrammetry and digital cartography group till February 2015, and he was Deputy Director of Data Processing Products, Archival and Web Application Area at National Remote Sensing Center, Hyderabad from March 2015 to July 2018. He was designated as Professor Satish Dhawan Scientist at NRSC Hyderabad for 2 years, from September 2018 to September 2020. In recognition of his outstanding contribution to ISRO at various capacities. He has received various awards, namely 5 ISRO Team Excellence Awards, like the first one for the year 2007 for his contribution to the Cartosat 2 mission. Second one for the year 2007 for the contribution in CartoDem, an ISRO project for development and realization of topography model for India using Cartosat 1 stereo imagery. Third one for the year 2008 for Chandrayaan 1 payload instruments, science, data center, and mission operation for integrated multi-mission ground segment for Earth observation satellites, conceptualization, implementation, and realization. Fifth one for the year 2015 for design, development, and operationalization of Calwell sites. He has also received Indian National Cartographic Association Award 2010 for the specific achievement during the year 2009 for lunar cartography, year 2013. He has also achieved ISRO Merit Award for the outstanding contribution for the year 2015. He was a member of International Planetary Data Alliance from ISRO, which evolves the planetary data standards for data archives in the global levels. He has more than 200 publications to his credit in national and international journals. He has 4 software copyrights. He is a life member of various technical societies like INCA, ISRS, IMSA, ISG, ASI, ISSE, and ASCI. His research interests include digital photogrammetry and mapping, geometrical data processing for remotely sensed data, planetary data processing, image Mosaicing, and stereo image analysis and pattern matching. So this is with this I'm overhanded. This is all about our guest of honor. Now I am handing over the session to our guest of honor to continue with the session. Thank you.
Thank you. Can I start?
Yeah, you can start, sir.
Okay.
Sir, you can start.
Thank you for the nice introduction. Sri C.A. Bhasha Garu, Chairman LIET, Mr. Syed Mahammad Garu, Vice Chairman LIET, Dr. C.V. Narasimhulu Garu, Principal LIET, and Dr. Shaik Mohammad Rasool, Head of the Department ECE, and participants, distinguished delegates, faculty members, good evening to you all. It is indeed my proud privilege to be here with you this evening as chief guest for the inaugural function of AICTE sponsored ATAL 2-week FDP on recent trends on signal and image processing with hands-on training using MATLAB at LIET. I would like to thank the organizers for giving me this opportunity. As I understand, the objective of the program is to update or train the faculty and research scholars from various engineering colleges with new techniques, approaches, algorithms, and methods in the area of signal and image processing with sufficient hands-on to enrich their depth and breadth of knowledge in these areas. This is a good opportunity which I feel the faculty can update their knowledge to impart better training to the students towards addressing some of the today's real life problems. I appreciate Lord's Institute of Engineering and Technology for the initiative of such program. This topic is apt as in today's digital world, signal and image processing play an important role in our day-to-day life. Signal and image processing is a vast domain covering various applications. To name a few, it has applications in medical field, biometric field, for access control, navigation, location-based services in geospatial world, sensor network, seismic, radar, sonar, etc. and etc. There are so many applications as today in computer vision and robotics. If you carefully observe last few years, this technology in signal and image processing has rapid growth in India, and it is being used to solve many real-life problems of the common man or citizen-centric applications, what I can say. To solve such problems and to provide an operational solution, a single field is not sufficient. We need to combine several of the above fields. For example, like a disaster monitoring or alert and the forest fire alert. All these things need not only remote sensing, there is a communication requirement is there, geospatial requirement. So several fields combined together, we can address the real life problems. In this context, as you all know, ISRO launched several remote sensing as well as planetary satellites, communication and navigation satellites. The data for use in many citizen-centric applications, as well as for land resource management, like agriculture, water resources, drought monitoring, snow coverage estimation, digital mapping, sand mining, weather monitoring, navigation, ocean studies, etc. In all these fields, you need image processing as well as signal processing together. So as you know, NRSA Hyderabad collects all the remote sensing data, processes and disseminates through its state-of-the-art technological portal. Today, we at NRSA has a state-of-the-art computer center where you can process 1,000 images per day, and it receives approximately 1 terabyte per day. Even in next 5 years, daily data reception itself is 10 terabytes. So you can imagine the data mining or data handling and data processing, how difficult or how complex it is. So you need to understand all the signal processing and image processing aspects when you want to use this data. The user can order any satellite data from this portal by placing a request. And the planetary data and science data from the satellites is collected at the Indian Space Science Data Center, what we call it as ISSDC, at Bangalore. And there, all the data like Chandrayaan-1, Chandrayaan-2, Mars, all other astrosat, all science data is processed there and disseminated from there. So any science data you want from satellites from ISRO, you need to request from ISSDC Bangalore. And when you wanted to, in fact, I wanted to just inform all the faculty members, you may be interested in interacting with ISRO and then take up some projects. So there are many channels. One is there is a respond projects. That means ISRO supports financially to the faculty or institutes for space applications, space science, and space technological related research. So through the Respond portal, you can always submit your proposals. If it is accepted, the financial support is provided. So you can visit our Respond site. You just type ISRO Respond, you will get all the details. So you can go ahead. And there is a Bhuvan portal where it's a geospatial portal. You have all the visualization techniques, visualization of the images, and you can freely download the data sets for your research. So NRSA has a lot of data and one can use, and you can always interact with ISRO through your research and development projects. In fact, NRSA has a cell called training and outreach. So you can interact with them. You can send your students for your project works, as well as you can take up research projects through Respond where financial help is required. So with this brief, in a short while from now, I will deliver a short talk which provides some insight of satellite image processing aspects, including some applications. Also, I will cover trends in image processing aspects and some of the challenges involved, so that what are the research topics, what are the trends in satellite image processing, especially since I am from ISRO and then I am specialized in satellite image processing. I'll be talking on satellite image processing. Otherwise, signal image processing is a very vast topic. Even image processing itself is very vast. So out of that, I selected satellite image processing because nobody will tell exactly what happens at the satellite image when you take it and then process it. So it is an important topic for you to just see how it happens. And also a glimpse of planetary image processing I will cover. So with this, this lined up with many useful and informative presentations and demonstrations, which will help you to understand some of the current and recent research works in the area of signal and image processing. At this juncture, I take this opportunity and urge all the faculty members to encourage students and tap the innovative ideas in science and technology through igniting their young minds. I once again thank the organizers for giving me this opportunity to be part of this program and share my research experience. And I wish all the participants best of luck in their future endeavors. Thank you. So now I will start my keynote presentation on satellite image processing. So I will share my presentation here.
Sir, you can share your PPT here.
No, PPT, it cannot go there because many links are there, which I have to put it from here. Okay. So whether the screen I can share, you can see that how I can share that.
Okay, sir. Okay, sir. Yes, sir. You can share your screen.
Now, is it visible?
No, sir.
Then how I can do it?
Yeah, now it is coming, sir.
Coming
yes.
now?
Yes, yes, yes. Please go ahead, sir. Go ahead.
Okay. So today's topic, I think people could hear me through phone I am talking about, but you are seeing the presentation. I hope so. Is it okay?
Sir, your screen again it went back. Sir, can you share your screen again?
Is it okay? Now it came?
No, sir. Wait, sir.
No, I have to do some share screen now somewhere.
Just now I mean, it has come again.
Okay, wait. So I have put it, but it may take some time, or what is that? I don't know.
Have you shared your screen, sir?
No, that's what. How?
You go to share screen here. Green.
1 minute.
Bottom, sir. At the bottom, it will be there.
Settings, reaction, and those things are there, but share screen.
The bottom, sir.
Bottom, sir.
Participants, chart, record, all these things. Green.
Participants, chart, live transition, transcription, reaction.
Rasool, I think you made him, sir, as a host.
Actually, sir, I gave the permission to everyone can share.
But what I have here is participants, chat, live transcription, reactions, setting, more.
Sir, can you go more, sir?
Rasool.
Yes, sir. I removed, sir. Okay. I have not shared my screen here.
But how did you get earlier one screen? You said no.
Sir, otherwise you do one thing, sir. You share me that screen. I will share here. At your PPT.
Right. That only I am trying. How to share the screen only I am seeing that, because
sir,
here I am not.
Otherwise, you mail him, sir. He will share here.
Mail or WhatsApp.
But then no, there are some links in between. I have to click. That's why I am not able to do that. I can mail it. I have no problem. But it is actually around 90 MB or something like that.
Okay.
But my video, in video screen, I am seeing my image. But why did this share screen?
Sir, will you please click on Alt plus S? Will you please click on Alt plus S?
Where?
Alt button
Alt plus.
on your keyboard. Alt plus
keyboard.
Press on S. Alt button will be there, sir.
Alt. Okay.
Yes.
Press it and then yes.
Yes. Okay. Share screen. So, but
yes, sir. Any window open, sir?
Nothing has happened. Alt. Yes. There is nothing is happening.
Like to save a document, we press Ctrl S. Similarly, for sharing screen, alternate is Alt plus S.
Okay, 1 minute. First, I will open my screen and then say yes. I will press Alt. Yes. Is it coming?
No, sir.
Earlier, how did it come?
Earlier, your mobile screen came, sir.
Okay, let me open. If I can open my mobile. No, mobile. I am not able to open this image because there are so many links available, which I have to press in between. That is where is the problem. But why this share screen is not coming in this is a question. All others are available buttons. Chart, reaction.
Sir, can you share your PPT to my WhatsApp? I will share here.
WhatsApp, it will not come 90 GB.
No,
MB.
sir, it doesn't come. Yes, 90 GB. 90 MB, it doesn't come.
90 MB, not GB.
Yes,
around
yes.
63 MB and with some links. But
Sir, you
I
leave
can
the
send a
meeting.
mail.
Can you please leave the meeting and rejoin again, sir?
Leave the meeting and
Rejoin again.
okay, I will do that once.
Participants, please bear for a few minutes. He is an excellent speaker.
Sir, we are waiting, sir.
Yeah. This is the problem with online.
This is the problem, right?
Yeah, if offline there would not be any.
Offline, I could deliver there itself.
Are you back, sir?
I'm just once again starting. Actually, the problem was joined from browser only. I think that it needs some update or something like that. Passcode 359224. 9224. Any Gmail is there? Otherwise, I will give that. At least without links, at least we can go ahead.
Yes, sir. You can send me, sir. Either me or Rasool or HOD you can send.
You give me your Gmail address. Gmail.
There's a Narasimhulu@gmail.com.
Continuous Narasimhulu CV.
Yeah, NARA.
Then I will send it first.
NARASIM.
NARASIM. Narasimhulu. Okay.
CV. At Gmail.
Yeah, it is there. I think your email is there in my box. So your file is larger than this. I will be sending as Google Drive link. Okay.
Okay. And also you send that Mahammad Rasool as the EC HOD also. Head EC also.
And I have already sent to you.
Yeah.
Just see that.
I will check.
Then you can open quickly. So one by one we can go through otherwise.
Yeah,
is it there?
Yes, sir. Yes, sir. Just now I received. I'm trying to. I'm downloading. Are you able to see my screen now?
1 minute. I will go through that.
Yes, sir. Yes, sir. Your screen is coming here.
My screen?
No, sir. Principal sir screen.
No, that you project it. So
Yeah. That's why I'm. A large data, no? It is taking time.
actually it has a lot of images now, so automatically
it is taking time. Yeah.
Okay. Now you can put it in a full screen mode.
Full screen.
You open one first slide. You open.
Yeah.
Now you put it in full screen mode. There is a full screen mode in the PowerPoint. In the left hand side, there is a full screen mode. Bottom
Sorry.
left.
You come right side, sir. Your right side, there is a option is there. Bottom.
more is there? Or you
No,
can
no,
continue, sir.
in the PowerPoint itself, there is a full screen mode.
Option I did not.
Can you use the slideshow, sir?
Yes, yes.
Ah, okay. Okay,
Now
it
you
has
can
come
continue,
now.
sir.
Okay, so I think, sorry for the delay, but we'll go through this now. So today I will be talking about, as I said, satellite imagery basically. So this is a very focused field, and I would like to tell what are the intricacies in the satellite image processing. And first I will give you some trends in image processing in general, so that you will know how the evaluation of the image processing has happened. Next, please. So historic perspective of image processing, if you really see what exactly we wanted to do in the image processing is, see, once you have an image, what you wanted to do, you wanted to understand. Basically, the image understanding is the process which gives you all the information. For that, image processing tools are required. So, in fact, image processing is also a part of signal processing only. Image is nothing but a signal. And so both are synonymously, we use images, sometimes signals. See, if you see radar image, in fact, it is a complex signal converted into the image. So if you go through the microwave remote sensing, actually image is not transferred. Signals are only transferred, which is converted into the image, and then you will use it. In between, a lot of signal processing happens. But in optical case, you take an image directly and then transmit it. So the interest in digital image processing methods actually from two principal application areas came. In fact, improvement of pictorial information for human interpretation. Finally, towards image understanding and processing of image data. Second application is for the storage, transmission, and representation for autonomous machine processing. Because earlier we used to have only the pictures in photography and printing and all. Today, in the digital world, you need a storage and transmission. So for this also a lot of image processing, meaning is compression and all, etc., required. And the digital image processing techniques evolved along with the development of computer technology. How the image processing has evolved through the computer technology, we will see in the next slide. Next, please. So now you can see that trends in image processing, how it has evolved with respect to the hardware. So in 1920s, if you see that first transatlantic transmission of an image, 5 gray levels only started, where mostly analog processing techniques were available during that time. There were no digital computers. And then 15 gray level representations on perforated tapes and photographic films during that 1920 to 1940. These are the things happening. Then in the 1940, when it came, then inception of data of a digital computer by von Neumann. In fact, digital computer was evolved in 1940, and then first transistor by Bell Laboratories, IC by Texas Instrument. So during 1940s to 1960s, machine language processing. Then once you come to the 1960s, during that, using digital computers to store and process images in the hardware side, it's the JPL NASA started. And the software side, first high-level programming languages, COBOL, Fortran, and used for processing images. And then main focus on image restoration and storage, because during that time, this Voyager and Ranger missions gave some images which needs a lot of image restoration, in fact. Then advances in storage technology took during this 1960s, and storing the images and all happened during that time. And inception idea to use image processing for remote sensing, medical imaging, and astronomy during that period. Next, please. During 1970s, the hardware development of microprocessors by Intel, then processing power for microprocessor began to rise with 8-bit microprocessors and C, C++, as well as 16-bit microprocessors enabling faster processing. This is the hardware side developments took place. So synonymous for that, as the hardware is developed nicely. So from the software point of view, the image processing side, computerized actual tomography, CAT, and advanced operating systems evolved. The algol used for image processing, procedures, image processing libraries are developed. Landsat imaging for Earth observation took place. Compression of images for laser transmission and X-ray imaging, enhanced images for bone structure studies, etc., happened during 1970s. Then when you go to the 1980s, the introduction of first personal computer by IBM, wide use of computers began during that time. And then tremendous improvement in digital photo making, and sensors started replacing the photographic films. Till then, all the photographic films were there. Digital sensors started coming during 1980s. Then applications like agriculture, cartography, geology, forestry, many things took place from the remote sensing images. A marked shift from image enhancement to image understanding and analysis began in the field of artificial intelligence to spread. In fact, use of personal computers computer applications to view and process images. Start of digital photogrammetry technique took place in 1980s. Next. So during 1990s, if you see that networking and inception of internet, then tremendous improvement in memory storage capabilities, 32-bit systems in market, and computers started becoming asset, personal computers, and use of supercomputers for medical and remote sensing image analysis. Point and the shoot cameras with the digital sensors, all are, I think, evolved during 1990s. So correspondingly, heavy use of images on web required browsing. All browsing and all started in computer. Then internet revolution brought advanced compression techniques to market. Several image formats like TIFF, JPEG were defined during this period. Then advanced techniques such as face detection and scene understanding addressed more accurately during this period of 1990 and 2000s. Then during 2000 era, continuous optics improvements, zoom cameras, ASIC-based processing, GPUs in the market, high-end gaming, virtual reality, advanced mobile phones with cameras started blooming. And correspondingly, computer vision for intelligence, Mars rovers, image processing systems heavily employed for factory automation and inspection, advancement and image processing software tools enabling high-end automated medical image analysis, super resolution and automatic 3D modeling suits using multi-view images. So this is what happened during 2000s. So now in 2010, when improvements in digital sensors for very high resolution cameras, octa-core CPUs, then trends in high definition images in this side, then software image processing functions on small handheld devices became common in 2010 to 2020. Then now if you see that 40 megapixel cameras on small devices, grid and cloud computing, and the software side augmented virtual reality, augmented pattern, automated pattern detection and scene reconstruction with world knowledge, machine learning, deep learning, and artificial intelligence techniques for image understanding. So in the future, when you talk about then high-end processors with built-in image processing facilities, the big data and data analytics today is the area, then complete scene understanding and classification, and the decision-making machines with capabilities to see and understand broad range of objects. This is what the future of image processing. I think this gives you a broad area of how the image processing has evolved. So I think you got some idea on that. Then now coming to the images, when you talk about digital images, there are so many images. If you see that gamma, X-ray, optical, infrared, radio, and even seismic and synthetic aperture radar and scanning electron microscope and this ultra, all are images. So image processing has no limit. Everywhere today in the medical as well as synthetic aperture or seismic, everywhere the processing on the images. So image processing become a very, very important for our day-to-day life. Next. So the other images I've showed, but the type of satellite imagery, if you see that, the first one is the panchromatic. Panchromatic means a single band image. So you can say the optical is my 0.4 to 0.8 micrometers wavelength. So if you take during that bandwidth, you can get a black and white image. But the same thing, you slice it into several bands and then apply different colors, you get a multispectral. The difference is you can see only black and white tones here, where the multispectral gives you so many, I think millions of tones which I can get. So that is the advantage in photo interpretation and classification. Then the down one is the SAR image, and there is a hyperspectral image. Hyperspectral means it is much more. So same visible band can be divided into 250 bands. So there is an advantage which I will talk about a little later. Next. So this is very high resolution image taken from Cartosat 2 image, Cartosat 2 satellite, our own satellite. You can see that buildings and their shadows. So you can easily see the very high resolution images means very fine detail you can see. But here, why I showed you this image, the important aspect is there are a lot of shadows, you can see that. So where the image processing, if you really talk about, can you expect information in the shadows? Because you only see the very black nature, but there is an information, there is an image. So this is the challenge, in fact, enhancement of the shadow regions. So that is the idea to show this image, but otherwise also very high resolution image you can appreciate. You can see the roads and then buildings very clearly. Next, please. So how image processing is changing our world today. Improvement in image processing have enabled major advances in wide range of technical areas, including biometric sensing, remote sensing, factory machine vision, driver assistant, driverless automobiles today, facial recognition, virtual reality, and many others. Okay. The future of image processing will involve, I think, distant future now, or we can say today, the scanning the heavens for other intelligence life. That is what is going on in the outer space. And if images come from there also, you can analyze and then see that. So next, please. So some of the applications, branches of image processing, as you all know already: image processing of remote sensing images, medical, high resolution images, stereo image processing, color image processing, computer vision, and microscopic image processing. There are so many image processing aspects, but I will basically touch on image processing of remote sensing images or satellite images, then some of the stereo imaging aspects, so that you can get much more understanding on those aspects. Okay, next. So as you know, this is the simple list image processing tasks, very basic things you all must be knowing already: that enhancement, restoration, mosaicing, fusion, registration, segmentation, classification, compression, super resolution. But these are the basic tools of image processing you can apply in, in fact, there is no generalized image processing that I can apply anywhere. Each image, what I showed earlier, needs some tuning to basic image processing tools, maybe same, but you have to tune according to your application or according to your image. That is your challenge always. So today I will focus mostly on image processing on the satellite images. What are the challenges? Next. Yeah, go ahead. Next. This is the actual principle of satellite remote sensing. You can see that. Yeah, go to the full slide. Like next you press next. Okay, stop. No, go back. Okay, so in fact, what is the principle of satellite remote sensing? You can see that it is actually the interaction of electromagnetic energy with the objects. This is a simple definition. Or in fact, remote sensing is remotely sensing the information. That is as simple as that. But in a scientific sense, it is actually the interaction of electromagnetic energy with objects. You can see here there is an energy source, that is sun. So it gives you the electromagnetic energy, and all the objects, something will be radiated, something will be emitted, something will be absorbed. All those things will happen, and the sensor at satellite, whatever it is, it receives the reflected energy or emitted energy or absorbed energies. So if absorbed energy anyway, you will not receive. Mostly you will receive the incoming EMR, and that is electromagnetic energy, reflected or emitted. And this is called the passive remote sensing. That means sun has the electromagnetic energy, it just gives. It's a passive. Active remote sensing is you send some signal and you receive back after the depending on its dielectric constant. In the radar principle is, depending on the dielectric constant, it will absorb something and reflect something. So the active remote sensing gives you some signal first and then receives the energy from the object. So that is the active. So here it is passive remote sensing, but in any case, so remote sensing principle is same. So yeah, the energy is recorded by the sensor, and it is transmitted to the ground station, and then the reception and processing is done in the computer, and interpretation and analysis for the applications, it is disseminated. So this is the basic principle of remote sensing. So next please. Hello. Okay. So when I think there is one more slide back. Okay. So this is how, when the satellite actually moves around the Earth, you can see the red arrow where that is called the swath, which covers continuously. It takes and gives you the picture. So you can see the detectors at sampling distance, and this is called the swath. Whatever it covers on the satellite, that is called the continuous swath of a certain length, depending on the resolution of the camera. Sometimes it covers 20 kilometers, sometimes it covers 180 kilometers, sometimes it covers, INSAT kind of satellite covers more than almost 1/3 of the Earth. So depending on the resolution and the sensor, whatever is put on the satellite, the swath depends. There is a high resolution cameras, low resolution cameras, large swath, small swath, and all those things. So this is the concept of, as the satellite moves around the Earth, it takes one full small swath, and then the Earth moves to the next position, and then second swath it covers. So like that, the full globe is covered by the satellite and the remote sensing front. Next. Okay, there are two types of satellites. No, back. There are two types of satellites. One is called the LEO, low Earth orbit, and then other one is called GEO. It is a geosynchronous. That is our INSAT and all. They are at 36,800 kilometers, where Earth rotation and satellite movement is synchronized. So always it sees only one place, the India, for INSAT. So that is because it is pointing to India always. There is usage of it is used for the communication mostly. But remote sensing also, like weather and all, also we will use from the INSAT. And low Earth orbiting satellites, which is 600 to 950 kilometers, it goes for the remote sensing satellites. It takes the pictures, so we analyze and then give all the applications. Okay, next. Actually, our one image acquisition modes we missed. Is it back? We will just go back and back. One more. Okay, image acquisition. This actually I wanted to show you the animation, but I may not be able to show because the other related files are with me only. Even if I put it there, it may not be. It has to be linked properly. So I'll just explain. One is the frame imaging. Frame by frame, it images. Then whisk broom imaging, left to right it will image. In fact, graphically it could show much better, but I'm sorry I could not show you that. Then push broom imaging, push and broom. That means each time satellite moves forward and a broom, it takes one image like that. One by one, line by line, it takes as it moves forward. Then step and stare images, that means it goes one step and then stare for some time, so that it will give you a high resolution. And the stereo imaging and wide mono imaging. Stereo imaging is actually like our eye is a stereo. That means left eye and right eye sees two different images which our brain emulates or simulates inside the 3 dimensions. The similar concept we use in satellite also. Take the same image in 2 different directions and simulate the stereo. Next. Next. Okay, go ahead. So this is how the high resolution satellites take the images, like there is a spot imaging. And that means today's concept is not to take the continuous images. For some applications, continuous images are required, like continuous monitoring of agriculture, drought and all you wanted to see, you can go with those satellites. Other high resolution satellites, you will not be able to take the continuous swaths. You can take patches, like one city located, 4 cities are located like this. You can take 4 different ways, tilting the satellite the way you want, and then you can take it that way. Other one is called paintbrush mode. That means the 4 different spots you can cover on the city, where the full city can be covered. Then multi-view means stereo kind of thing. That means in one angle you take one picture, and second angle you take second picture, and create a stereo. So these are the various ways one can take the pictures and then use it for your processing. Next. Okay, this is in a nutshell. If you see that the whole processing aspects, like satellite gives the data to the ground station and data acquisition ground station. Then data processing takes place. Data processing involves pre-processing, radiometric correction, and geometric corrections. I will come little later. All these things, you can see that it is increasing in information as pre-processing, radiometric, and geometric. Then you add value to that to make use of this for the applications, like digital elevation model creation. You can create maps, you can generate merged products or combine the information, you can do a classification or segmentation, you can do a mosaicing and then geophysical products. So then the whole data after processing, you archive, browse and disseminate and to the user community. This is what it happens at NRSA. Precisely this diagram, whatever I am showing you, this is how it happens at NRSC. So you can request a data user community, and then you can get the data of your interest. And that data you can take and you do your value addition, or value addition you can request to NRSA as well. Next, please. So in the satellite image processing, important tasks are, say, basic enhancement restoration will be common. There is image rectification is the one what you need to do. Then mosaicing, why you need to do? Satellite gives you a fixed swath, like 20 kilometers, 40 kilometers, depending on the sensor. But Hyderabad, like city, suppose there is 60 kilometers width. So you need to take 3 pictures side by side and mosaic it. Mosaic means stitching. Then that is a great challenge when you do image mosaicing. Then registration, and registration is required when you wanted to do a change detection. Suppose today 1970 how the Hyderabad is there, and 1980, 1990, and if you wanted to see, you need to have all the images and then register and see that, so that how the urban is developed, or how the water bodies are vanished, or new water bodies have come. To do all those things, you need a registration. Then fusion means you can fuse to information. Then you get a different kind of information. A low resolution and high resolution you can fuse to get the high resolution multispectral data. Then segmentation, classification to assess the particular signature, how much it is there, how much water is there, how much agriculture is there. It is for that you need to segmentation and classification. And image compression, it is for the storage and then transmission from one place to another. Next, please. So it is a standard thing where already image enhancement, spatial domain techniques are there, and then frequency domain techniques are there. This is basis which but how the same techniques we use even satellite image processing also, not too much of different. But satellite image processing, what we do is we try to understand the sensor and then use the technique accordingly, or multiple techniques. So you can easily see that depending on the specific task, image content, observer characteristics, and viewing conditions, we can have a different kind of parameters which we can tune it. Okay, next. Here I wanted to emphasize what in the satellite image processing, what kind of new techniques what we use is the dynamic range adjustment, which is better than your contrast enhancement and edge detection. They are standard tasks, but standard tasks fail in certain cases where we take the image in principle itself into the consideration of the enhancement and then we use it. Okay, go ahead, next. Okay. Dynamic range adjustment option, just wait, will be useful for the following users. Users who don't own software required to apply a contrast stretch, expensive software, or who don't have extensive remote sensing expertise, users who don't have time to apply stretch to the data, yet need to do for a visual interpretation, users who are interested in product for visual purposes, for web display and all. And it consists of conversion to spectral radiance. Actually, radiance domain we do this instead of digital numbers. First, radiance domain we convert it and then do the required stretch, and then come back to the count domain. So path radiance correction with nonlinear contrast stretch. So this is a specialized kind of dynamic range adjustment technique which we use for the satellite imagery. Next, please. You can see the literature, some more things are that illumination based stretch and all, which are similar to this in fact. You can see the left image, which is linear contrast enhancement, which you are much familiar, but a scene which is having very low and very high dynamic range kind of features, then linear enhancement will not give you the ideal enhancement. So you can see the right hand side, dynamic range enhancement, the lower feature also is enhanced and then upper feature is also enhanced. This is the importance of dynamic range stretch. Next. Here you can see that Bangalore image, which is Vidhan Sauda. You can see there is trees are there and then buildings are there, which are even linear contrast stretch will give you left side, which is still darker. If you try to stretch too much, then it becomes actually the saturated. Buildings will be saturated. So we use the dynamic range adjustment. You can see the right side, which are fairly very nice picture where both ranges are enhanced. Even histograms show that dynamic range is adjusted properly. In close look, you can see that very nice enhancement is taking place. Next. And this is another one. You can see that this dome kind of thing in Bangalore. And in linear contrast stretch, if you do, it is totally flattened or very bright. But now the right side, if you see, it's nicely enhanced in the sense both contrasts are maintained properly. Even the down, you can see that there are very nice small features one can see very clearly. Next. This is another railway station, Bangalore railway station. If you see that, that's nicely enhanced. Otherwise, the left side is linear contrast stretch, which is actually very dark. It is called the photo response non-uniformity, because photo response non-uniformity, before we launch the satellite in the laboratory itself, we characterize the device. So what we do, a standard response we take for each CCD, we characterize according to that standard response. So when the satellite gives you the image, each pixel now will be transformed according to the standard response. So you derive a gain and bias with respect to the standard response for each CCD, then apply after this you receive the data. So you can see that left side is without photo response non-uniformity, right side you can see that photo response non-uniformity. See, this is the kind of enhancement what we talk about in the satellite image processing. Next. This is another thing is device stagger is there. See, we don't get, if I want a 12K device, I may not get in the space qualified device. So normally we get 6K device, which two staggered devices we keep it. All even and odd are separated by 5 pixels. So two 6K devices, we put it electronically, and then what we get images like left hand side image. There is a two kinds of small staggering will be there. which you need to understand and then correct. So in satellite image processing, what you need to understand is always the satellite, the characteristics of the sensor first. You have to understand very carefully, then apply all the image processing tools. So it is each time is the challenge. If there is new satellite and then new enhancement tool, new restoration tool, which you need to develop. Though the basic principles may be same enhancement, but the underlying principles, underlying parameters, which you need to tune very carefully, then you will get that right side image. Next, please. So now other trends, these are the basic things which you know, but I gave you 2 examples of image, satellite image enhancement. But otherwise, literature, what it says for the future trends or current trends, if you see that combination of various techniques, what I have gone extensively the literature where hybrid techniques are used to get a better result for the particular application. Sometimes you use a frequency domain first and then make a spatial domain, and then that kind of hybrid technique you can use. And there are many, depending on, I think, suppose underwater imaging, when you say it's very low illumination images, you need to have a different kind of techniques. Then wavelets are being used for better enhancement of images. And then future scope is, in fact, adaptive algorithms for effective image enhancement using machine learning, fuzzy logic, and neural networks. There are so many reviews which I have seen in the enhancement where these are the upcoming and research areas which in the enhancement people use. Next, please. This is about the enhancement. Now we'll go to the restoration. Next. So the basic thing in the restoration, when you talk about an image, so now you have to understand how the image is formed first. Then only you can understand what are the degradations within the image. Whatever I talked about is earlier is enhancement. There is a very subtle difference only in the image enhancement versus restoration. In the restoration, what we talk about, what are the degrading elements in this image formation itself. You can see this here. Imaging optics comes into picture, detector, A to D converter, and there is a compression. And there is a platform and platform attitude and motion. So these are the components while image is getting formed. So you can understand image optics has some transfer function. So it will not give you anything one signal gives, one signal goes into that. Exactly, you cannot reproduce. As a signal processing man, you know that no signal will be identical when it goes through a system. It has, in fact, modulated by the system transfer function. So system transfer function is the important thing to restore the image back. So one is here, if you see that imaging optics is one thing, then detector comes. There also it has a transfer function. A to D and compression has no much of image degradation immediately. Compression has, but that restoration is different. And platform motion, as satellite moves, Earth also moves. And together there are too many motions, so there will be a blur. When you have a motion, you have a blur. So you have the focus problems. Then platform attitude, that means as any moving body will have roll, pitch, yaw. That means forward motion, side motion, and rotation. So these kind of 3 motions come into picture. So all these things cause a lot of degradation in the image. So how to tackle these things under the image restoration? You can see here, if you see the images what I have given in the down, there is a modulation transfer function or transfer function, which you can say a combined transfer function you can be estimating as MTF as optics, MTF detector, MTF motion. These are the 3 main components. So MTF optics is precisely known where you know what optics you are using and also transfer function is known. Detector also know, but platform motion is different for each satellite. Platform motion is different depending on the satellite as well as its orbit, as well as the Earth rotation during that time, depending on its swath. So that has to be characterized, and that's what we do in ISRO for characterizing. This is the toughest task. In fact, improving the image for all this degradation is the great task, which one has to learn by experience or by so many satellites, so many sensors and all. Okay, next. So this is a general image restoration problem, recovery of estimate of original image from observation, as you know that. Then this is required for high resolution data. Actually, for low resolution data, image restoration is not a big issue, but high resolution data only, because very small details, it will be blurred. So you need to get very precisely those details. So techniques to remove systematic degradation is by denoising and deblurring. So these are the hot research topics today. In fact, denoising, you can see thousands and thousands of papers, and deblurring also. So denoising based on edge preserving techniques, because when you do a denoising, edge may be affected. So the ingenuity should be denoising based on edge preserving techniques, deblurring based on sensor point spread function. These are the issues which we need to tackle in even normal images as well as satellite images. It's much more. You can see the Cartosat 2 image. One is the top one is original and then restored. I'll come back. Next. This is a spatial responsive imaging system. You all know as a signal processing method. G is F convolved by HXY plus NXY. And so imaging model frequency domain GUV is equal to FUV and HUV. So precisely what we need to do is we should have a knowledge on HUV and noise characteristics. If these two we have, we can have an estimate of FUV. That is what is the restoration problem. Next. So F dash UV is equal to RUV into GUV, where RUV is equal to 1 by HUV. That is transfer function. So pseudo inverse filtering means simply you can divide by HUV, but HUV dividing will have a ill conditions, because suppose sometimes inverse filtering leads to absurd results as HUV approaches to 0. So usually we approximate 1 by HUV plus 1.0. That is what pseudo inverse filter we call. We normally design in satellite image processing. Wiener filter we found out more suitable, where I can tune my noise to signal ratio according to a sensor, then use it. Good. Okay, next. So these are the certain results with one of the satellite imagery on the airport strip. If you see that photon noise removed and then inverse filtered, and see that right top. Inverse filter is always will be a problem, because there will be always tending to zeros will be there, which creates problems. Then Wiener filter down is with noise to signal ratio, exponential model, various things. So you can see the certain improvements, but the further improvements you can see. Next. This is the filter performance. You can see the left is the blurred image, and then Wiener filter with the noise to signal ratio is equal to K into exponential T tau, where K and this T will be tuned accordingly. K actually is tuned so that I can get a best performance. And this K will dependent on each sensor and each thing. That we initially we take few images and then characterize and then come back with a particular constant, and then we give it for the operations. Next. So this you can see now how it is better restored. You can see very clearly that 3 lines are blurred in the left, and then they are very clear in the right, even other things also. Next. This is very clear. You can see left and right with using the restored images. So this is one of the tasks which we go through in image processing of satellite images. Next. You can see here some more images. Next. And second point in restoration is noise characterization and removal. Adaptive signal estimation approach we used is a 1985 paper, which actually suits to a satellite image, where normally we estimate the noise from the signal itself, that means image itself, that is sigma square, and then use it for the filter, the local variance using adaptive weights, and this gives you the best approach. Next. You can see that the top there are 3 bands. Each band is noise removed and then down, and each one gives you a very nice picture. This is a purely noise removal algorithm, whatever it is, adaptive noise removal. Next. And this is actually the Chandrayaan-1 moon impact probe image. You can see that top there are so many small dots, which are actually the periodic noise, which we have experimented frequency domain filtering BLPF and notch filter, Butterworth low pass filter and notch filter together gives you the best result. And in both cases, we have many moon imaging probe images. When Chandrayaan-1 was launched, there is a probe which is actually hit the ground. In between, there are so many frames it has taken, and we have restored that and then stored it. Next. And other trends in image restoration is wavelet-based image restoration is becoming more and more prominent, and image denoising using curvelettes, which is edge preserving, and blind deconvolution techniques, blind image super resolution reconstruction, use of neural networks for noise removal. These are the research areas and then trends which is going on today in the image restoration. And image restoration is also the hot topic continuously. For high resolution, it is more challenging than the low resolution. Next. So image rectification, when you talk about when satellite image is given, what happens it is, it has so many noise components, what radiometrically we talked about already. But when satellite moves, Earth also moves. There are Earth rotation, Earth curvature, terrain effects, and platform effects. There are so many effects. So whatever image you get, it is not true to the ground. See, today you see from the Google map exactly what is the latitude, longitude. How they have created or how we have to create is not just satellite raw image will not fit into that. So you need to position each pixel exactly to the ground where it maps. Then only there is a meaning. Otherwise, there is no meaning. Image rectification is important because if I have given you an image, you never know what it is. That if I give you a latitude, longitude attached to that, you can tell what image it is. That so that means ground tagging is more important. Ground tagging, how do you do? You have to understand what are the distortions present in the image. You have to rectify and make it each pixel matching onto the ground, whatever is viewed. So there are so many. These are the so many distortions which we need to address in our satellite image processing. Next. So geometric distortions of satellite imagery. Here you can see that image motion as satellite moves, how roll, pitch, yaw will affect each scan line. So this kind of distortions which will be present, which we need to understand and then correct it. Next, please. And this, how do? We do through a collinearity conditions. That means it is a three-dimensional geometry, understanding the pixel to the ground. You form a three-dimensional geometry having so many coordinate systems in between, then try to match with the ground. This is a complex thing, but you don't need to understand too much on that. You only understand that image to ground, how to tag it. I have an image point, that means one pixel, where to tag onto the ground. That understanding is done through these equations. Next, please. This tells you, so image is right side picture, if you see, ground is this the ellipsoid, that is Earth, and then image is on the top, which are the dots are the pixels. So a collinearity. Collinearity means what? Ground, satellite position, and detector are on the same line. That is the principle what we use to correct the previous equations. Now you can see that the ground, this right side box, blue box is the ground. For each ground pixel, I have to take through the transformation this pixel and put it here one by one, and then it will be corrected. Next. Now you can see that the uncorrected image in the left, which looks like rectangle, but geometrically corrected image, you can see that it is rotated. Why it is rotated? It is actually the Earth rotation looks like that. From the top to bottom, when the satellite moves, this much Earth is rotated so that it has to tag onto the Earth to the corresponding pixel. So there is a scale, there is a rotation, translation, all those things we have to correct through the equations. So this is a complex process, which is image rectification. Next. And this gives you a clear picture. Now you can see that there is a original image radiometrically, then geometrically corrected. Then you can apply a digital elevation model to fully correct it. So you can see this bottom right also, roll pitch here, corrected image, and then these things. And the bottom left is actually the misregistration. If 3 bands are little bit misregistered, you can see different colors here. Whereas once the misregistration is corrected, you get the correct image. Next, please. Another topic is hyperspectral image processing, because here you get a very challenging task of image processing where hyperspectral means what? The same spectrum, that means some 250 bands you can divide, and each band you can collect the information and combine the information to get various applications. But you can ask that why, what is the big deal in this? You go to the next slide. This is a spectral signature. So suppose if you see the soil or anything, the wavelength versus its reflectance, this is characterized by the spectral signatures. Now you can see that. So in one of the wavelengths up to 0.8, let us say visible wavelength, if you see that water with clear water signature is something different than other water, turbid water. So if it is only 0.4 to 0.8, I'll get only one signature. One signature means 1 pixel for the water, which will give you average response. But whereas if I divide 0.4 to 0.8 into several sub bands, then what happens? The peak will come at 0.7 or some 0.5 or something, where high reflectance will be there for that band. Like that. So you can easily discriminate water at that band because it's highly reflected. Like that. If you at 0.8, if you say it is very low. So this way you can interpret with multiple bands of the same signature. But what is the disadvantage in this? As the band narrower bandwidth, if you take, your signal strength is very weak. So there is a compromise. You want high discrimination, then you can go to hyperspectral, but it will have a lot of noise and signal strength is poor. So you have to handle these things in the multispectral, hyperspectral remote sensing. Just go back one. But the advantage of hyperspectral is you have so many signatures. You can combine different bands to get a very different applications, like monitoring health of plants, and then agriculture in detection of animal proteins, and then biological and chemical detection, precision agriculture. There are so many important aspects, but the research topic here is which bands you have to combine or how many bands you have to take to get a particular information, because you have tremendous number of bands, but which bands to combine to get a optimal information is the research topic. So the selection of bands is one of the important topics. Next. This stereo image processing we will deal with next. So stereo means what I told you. The same image taken at 2 different directions. As your eye also sees 2 different directions and then emulates the 3rd dimension, the same principle will be used here in the satellite. So you take in 2 different directions, 2 different angles, same images, and reconstruct the height. That is the principle of stereo, which is very, very important, because you need to construct the 3rd dimension. When you wanted to have a building height, and you cannot do survey of all the buildings. No, you can use the satellite or high resolution satellite, and 3-dimensional information you can do derive through the stereo imaging. So, and you want to have a digital elevation model, or you wanted to put 2 cell phone towers, you need to have in between what are the obstacles. That means what are the heights obstructing it. That so a digital elevation model generation is very, very important, which the high resolution images of stereo will help you in generating a digital elevation model. And digital elevation model is important because all these Google images and all, if you wanted to get a true scale, you need to have a digital elevation model and correct it to the scale. Then only you will get. So this is important. Next. Okay. So these are the Chandrayaan-1 triplet imagery. That means one looking at 4 center, one is looking at Nadir, other one is looking at back. So 3 ways of looking in Chandrayaan-1, where you have 3 dimensions you can create between 4 and Nadir, or Nadir and aft, or aft and 4, or you can use all three to get a digital elevation model. So next. So this is a simple way to deal with stereo image processing, where you have a model which I have shown you, image to ground model, and there are ground control points, some important points which you have to take in the image on the ground together to tag with. Then image processing task is image matching. That means left image and right image, when two images are taken, the basic principle is the same point you have to locate from left image and right image. Then only that can be that can be used for generating the height. So that is the basic principle. So you can leave all other things, but image matching is the important aspect in terms of image processing, because there is a lot of research going on how best you can do, because there will be a lot of mismatches when you talk about an automated way of doing. And each pixel, when you talk about 12K by some 1 lakh lines, if you wanted to match left and right image, supercomputer also will take a lot of time. So you need to have strategies to do a image matching. So a lot of research is going on in this also. Nobody has achieved 100%, but everybody reaches 95, 96 or 97. And there are other methods which to deal data which are blunders you can remove. There are so many strategies people follow. So this is another research topic. Next. So this is a hierarchical matching, what we call. So you take the pyramidal approach. So you take the full image and then compress by 2, compress by 2. Compress means just eliminate 1 pixel, alternate pixels. So you go to the last level, some 32 levels you go. The last level you can first match, which is simpler because it is a small image. Then that information you use to the next level you populate. Progressively you go to the hierarchical matching. This is what we have implemented in ISRO, where we generated digital elevation models of the whole country as well as Chandrayaan whole moon using this technique. Next. So the challenges in image matching is multi-temporal seasonal changes of ground features. Sometimes it pose a problem, and different view angles pose problem, and then scale changes pose problem, and radiometry and resolutions pose a lot of problems. So these are the basic challenges. Next. So here relationships between the matching methods and matching entities. You have matching method, area, feature based, similarity measure, correlation, least square matching, mutual information. Mutual information is the best, which normally you can use. And then matching entities, you can use gray levels, interest points, edge points, relational description. Feature spaces used in image matching, raw intensity, edges, so many things. Next. Similarity matrix used in image matching. You can use there's so many: normalized cross correlation, correlation, statistical correlation, phase correlation. So you can just imagine how many are there, how much research is going on in various combinations. In this, we have used set strategies as hierarchical technique. Otherwise, wavelet based feature matching is also there, object based matching. There are so many. So there's a big list which I have given, which we have studied and then gone to the hierarchical techniques. Next, please. Okay, this we can skip because next you can go to the. Okay, wait. Okay, we'll just explain. Say the topmost, you just do a correlation, then transfer the information, then local mapping between them, and then correlate. Like that, it keep on going into the next level. Next. So once you have got match points, next. Next, please. Next. Wait. So left side, you have matched points to right side. So corresponding point is there. For each point, the collinearity condition is defined. And wherever in the space it matches, that is the height point. Like our left eye and right eye, the ray, wherever it intersects, it gives you the height. So the same principle here, we call it as space intersection, and you will get the height or depth of the image. Next. So this is the digital elevation model of a particular full scene stereo pair, what we have taken. Left side is the digital elevation model, right side is the satellite image. You can easily see that wherever the black portions are there, it's a low elevation. wherever bright portions are there, they are high elevation. You can see in the right side image, it is an image. The black is the hills. So that is correspondingly white in the elevation. So you can easily see that. Next. This is a Gangtok digital elevation model. Here also you can see that black is low elevation, that is valleys, and bright is the hills. Next. This is the full India digital elevation model which we have generated and kept it in Bhuvan, our NRSC website. One can download and use it for your reference. The full India, Pakistan, and Afghanistan is a full which we have generated. It's called Carto DEM version 3. This is from our Cartosat satellite. We have taken the stereo pairs and then generated the full DEM at 10-meter interval, at 25-meter interval as well. Next. These are various applications. When you have digital elevation model, you can make a city model, you can do a mapping, you can do the visualization, etc. Next. You have always a confusion, but there is a digital elevation model, digital surface model, and digital terrain model. So this always comes into your mind. And this is another topic, how to derive digital elevation model from digital surface model, because whatever digital elevation model what we are talking about from satellite, it is a surface model, because on top whatever is there we can see the canopy and then take the height. But actual application what you need is the digital terrain model, is a bare earth model. Our maps and all talk about digital terrain model. So what you have to do, you have to eliminate or you have to remove all the man-made objects or all the canopy and all, then you will get the bare earth model. So you can go to the next. Here you can see that the top, this is all called the digital surface model, right side. Digital elevation model is left side. It's only the ground level. But the image processing involved in this is the generation of digital elevation model or terrain model, both are same, from digital surface model. Whatever we derive is digital surface model. So what we need to do, we have to eliminate all those objects. You go back once. So you can see that left side is rough because buildings and all are there. Right side was smooth where bare earth is there. But this is an interesting topic where you have to do a segmentation and do all the buildings and remove those things and put an average height there and make a digital terrain model. This is another research topic one can in fact address. Next. So once you have a digital elevation model, you need to create an ortho correction, because if you wanted to really see the true lengths and true heights in the Google image and all, when you wanted to go from one place to another place, the distance calculated is the surface distance. So for surface distance, when you want, you need to have the elevation intact. You can see here in this picture, if it is orthogonal versus perspective projection. Satellites give you the perspective projection. That means it will take a cone as like this. Actual cone should be a concentric circles, and you see from the top. That is the orthogonal way. Each point individually you see from the top, it is orthogonal. But in the satellite and all, our camera, we don't see individually. There is a focal plane where you can see here very clearly A, capital B distance in image, it's very small, and capital B and capital C, it is large. It is all because depending on the elevation. So if elevation is not there, both are same. So the elevation is playing an important role to find the distance between the pixels, what it is imaging. If it is highly elevated, there is a lot of error. So that you have to correct, where the digital elevation model, what you have already generated, should be used to correct it. Next. So this is what, once the digital elevation model is there, you project it and correct it. So that is how you generate the ortho correction. This is just to give you a output input mapping and an ortho image generation. Next. If you don't do the ortho correction, now you can see that ortho image, all the map contours and all are matching very well left side. if I don't do the ortho correction, the height differences, the contours are somewhere and then the image is somewhere else. So this is the difference, and this is the error what you get between the contour to ridge. That much error you will get in the distances, and also you need to have an ortho corrected image always. So whatever images you see in the Google and all, it's all ortho corrected so that your distances and everything, scale, everything will be matching. Next. So this is a visualization. Once you have a digital elevation model and ortho corrected image, you can sit in your computer and then you can see various glaciers and then how to go about around that and all. Very conveniently you can do. This is called visualization techniques, where perspective view you can create from ortho image and DEM. You can create various views and then assess the rigidity or the complexity of the terrain and all. Next. In fact, I have so many videos which I may not be able to show today. And this is a Chandrayaan-1 image strip. You can see that crater. Normally we see it is actually pseudo. Normally when you see the image, it comes out as if it is a hill, but it is not so. Now you can easily see that once DEM is put and then visualization is there, it is actually the big, in fact, pits only, very big undulations. Next. Quickly we'll go. This is another Chandrayaan-1 image, a full strip image. It's a digital elevation model generated, it's contours generated, and it is color coded. So you can easily see that the black is the lowest elevation and then bright is the highest elevation. Contours also show the same way. Next. And this is a map what we have generated. This is the first of its kind from our own satellite. Nobody has created as yet, kind of thing. Lunar Atlas. We have created from Chandrayaan-1 so many maps like this in all the wherever the images are there. You can easily see how best we can use this for navigation. Next. And this is a visualization, a small crater. The height, if you superimpose, how you can visualize. Next. This is Chandrayaan-2 crater, very recently imaged. Next. And this is also Chandrayaan-2 images and digital elevation models. Next. This is a high resolution camera from Chandrayaan-2. You can see that very small boulders along with its shadows. It is actually the 25 centimeter image, 25 centimeter on moon. You can see these boulders and all. This is called OHRC, optical high resolution camera. So this is the highest resolution imagery as on today. Next. And another topic, as I told you, is image registration. Image registration is simple, where you have to find two images, they have to be registered. So you find common points, which I told already, the matching techniques are used, the same matching techniques used, and build a relationship between these two and match it. But here you can see in the animation, many features on, here it is some 5-6 images are overlaid. In some day, some features are there, some days some features are not there. So change detection you can easily see in this animation. So for that you need an image registration. So that means pixel by pixel you have to register as a time series. Then you can see the changes. Next. Anyway, these are the components involved: feature detection and feature matching. This is same thing as what I have told as image matching. Next. So if it is misregistered, it's the left side. After registration, you can see that it is right side. It is image, that is band-to-band registration. Next. The next one is image mosaicing. Next, you can just next. Okay, wait. So no, back. So in the image mosaicing, the important task is first register two images in the overlap. Mosaicing is means what? You have to stitch two images. For stitching, you need a common area. So here, first you correct it and then do a polygonal regeneration. Which polygons you have to stitch? That is what you have to find out. This is a graph theoretic approach. and the image stitching is done by minimum cut algorithm through a graph theoretic approach. Then once you stitch it, the radiometrically you have to adjust it. Okay. Okay, we'll go to the next. So these are the three images, let us say side by side. They are radiometrically different. Left image is something radiometric, right in middle is something, and right is something. But all we need to combine to get a single image. Next. So next. So now what you know, it is step 3. You go back, step 2. Not coming. Go back. Okay, the other 2 images have not come, but okay, go to that step 3 then. Next. Okay, this is what the image mosaicing means. All 3 are combined with all the radiometry and everything is set together. So this is called image mosaicing. But image mosaicing is challenging when high resolution data is there, where buildings are there. How you will stitch one building looks in one image left side, another image right side, the same building. So there is a challenging task in high resolution imaging. Here you don't see buildings, only roads and all. It's a low resolution. So mosaicing will be much easier. But just for an example, I showed you. Next. Next, please. Yeah, next. Okay, this is the point of contact, but the graph cut algorithm selected where to join. In fact, that's what I wanted to show. But next image will give you more clarity. Next. This is a left image. Next. Now it is connected. So you will never know where it is connected. This is the power of the graph theoretic approach in the high resolution. Here all the buildings and all are there. You don't know where I have joined. So the joining point, that is the graph cut algorithm, will decide according to the, it will avoid the buildings, and then you see that wherever the low intensity is there, and then where I can join. This is a, with intelligence, it has to do it. Next. Next. It has also joined that way. So accordingly, so here you can see, but this is not a small problem. This is a very complex problem. One has to understand, and then you can take up as a research topic as high resolution mosaicing. Next. These are perspective images mosaicing. 2 images perspective. Then you extract features and match filter using ransack and transform and blend. So 2 perspective images, how to do a blending and then mosaicing. Next. Then comes the image fusion. These are all value additions, and then next please. So here there are so many approaches. Image fusion is a process of combining information from 2 or more images of a scene into a single composite image that is more informative and is more suitable for visual perception or computer processing. What I mean here is, you have a high resolution panchromatic data, 1 band. You have a low resolution multispectral data, 3 bands. But if I combine the multispectral and high resolution, both, what I expect to get is high resolution multispectral data. So I will save a lot of link for transmission, because if I transmit high resolution multispectral from the satellite, it takes a lot of time. But on ground, I only one panchromatic I transfer, and 3 multispectral, which are very small images. Together I combine and then get a high resolution multispectral. So there are so many techniques: pixel level image fusing, modulation based image fusing, component substitution, that image intensity, hue saturation, principal component analysis, Gram-Schmidt. There are many algorithms. Here also a very good research going on, where how to preserve the high resolution and how to preserve the color composite. This is the challenge. Next. So here there are the 2 things: Cortex at 2A, and that is 0.8 meters, and this 5 meters. 5 meter color is right top, and 5 meter black and white. It is a high resolution. You can see all the buildings and all. But in the color, it is 5 meter, and black and white, it is 0.8 meter. So that's why it is very clear. But color information, now I have to merge it to the black and white. So these are the various techniques which we have used. Now you see the bottom left, bottom, okay, right. You can see that how the color component is emerged with, this is called natural color composite. Next. You can see various methods. These two combining this, and then DCT, CT, and then various SDM, CSA. Okay, I will go to the next wavelet based. This is the data fusion using wavelet based techniques. We can say the high resolution pan and intensity component of our multispectral. Intensity, hue, saturation you take, and intensity you take, and then wavelet decompose, and then wavelet decompose. Then you combine this LL2 here PL, then do the recompose, and then get back. So pan and LIS3 merged together. Pan is 5 meter, LIS3 is 23 meter. Now you can see that pan plus LIS3, the 5 meter multispectral, how good it is. You can see that after, it's almost like original 5 meter multispectral data. This is the power of data fusion. Next. This is another thing, Cartosat 1 and RIS4 and combined, and you can see that merged product. Next. This is another. Next. These are the various examples. Now I come to the briefly some quickly some case studies what we have done in various cases, but quickly we will go through. Anyway, my presentation is there, which you can always see that, but let us go through first. Next. I may take another 10 more minutes. It's okay, Dr. Narasimhulu.
Sir, then we will be having interaction with the participants.
Another 10 more minutes, no problem. Then interaction also we will have by 9:30.
5 minutes, sir. You try to find up 5 minutes, sir. Within 5 minutes, then we can have it.
There are so many.
We have only 10 minutes time.
Okay.
9:30
we have delayed so much. Okay. Okay, sir. Okay. So then just I will tell you that there is a time series, in this case simulation of multi-temporal resolution. Here what I wanted to say is you have 5 images top, AVIFs, that is called 800 meters by 800 meters, and bottom you have only 2 days, that is day 1 and day 5. How to simulate the remaining 3 is the deep learning and machine learning technique what we have used. Okay, next. Next, please.
I'm trying, sir. It is not
moving.
Up to here only.
Why?
Till now it has come. Maybe is it? Okay, now it is.
Okay, it is coming. Anyway, this is the process how we have done it. Then we will skip it. Anyway, you can read later on. Next, I will show you the results. These are the results. Suppose AVIFS is 800 kilometers by 800 kilometers. It is available in all 5 days, but this 3 is available only first day and the 5th day. In between, you wanted to create using the machine learning techniques we have created and compared. It is mostly 87%. It is matching. That is what is the result. Next. And another thing is creating the remaining portion. That is, this 3 is 144 by 144 central portion, but AVIFS is 800 kilometers by 740 kilometers by 740 kilometers. How to create the remaining portion is using once again this is machine learning techniques only we have used and then created. Next. Next, sir.
Sir, try this one. Stuck out in the maybe.
One by one, it is not going.
Sir, otherwise we'll take interaction session.
Okay, fine.
It is not moving, sir.
I
But
request.
I can open.
Yes, sir.
I can open, but you will not be able to see. That is the problem.
No issue, sir. So
No,
I
but
request.
what I will do, I will open and then something. If not, I show the images. I will at least speak something to conclude. Okay.
Unable to open, sir. Unable to go further.
Okay. What I will do
Conclude,
is
sir.
I will go to that slide. I will not be able to show you, but I will speak certain things where we can conclude. Okay. Okay. I will speak. No problem. But if you are not opening, don't bother. I have only few slides to show. See, using machine learning technique and deep neural network, what we have created is the image simulation we have done, oil spill detection we have done. Then there is a challenging topic called super resolution of DEMs, like super resolution of images you create, super resolution of DEMs, one can do it. Then there is a framework, what one can take up as a research topic is the big data plus machine learning, and as a framework one can take to get a better day-to-day predictive models. That means one small example I will give is, suppose I have seen the water bodies diminishing from 1970 to today over Hyderabad. I have all the data set, but I can predict using this machine learning technique, next 2 years, what kind of water bodies will be disappearing, so that I can give an input to the ministry or somebody. So these are the real life problems, like sand mining is going on somewhere, or water is depleting, or snow is melting. These things, if you wanted to see the previous data, we take a lot of remote sensing data and then learn it and then go to the predictive analysis. This is a big data plus machine learning framework one can create. Then for this applications are rate of change of water layer, crop monitoring, rate of change of mining, you can say forest cover monitoring, you can say forest fire monitoring, urban growth time series analysis, all those things you can do it with the time series analysis. Okay. Then some of the challenges I will just read out. We'll finish anyway. Enhancement of shadowed portion, which I have said. Image matching and registration is one topic, and automatic feature identification in HR, high resolution images, data fusion, image simulation, super resolution, high resolution image mosaicing, 3D city models, 3D modeling, cloud and distributed computing, and microwave data processing we have not addressed, but that is a challenging topic. Then some images are there here, Chandrayaan 2 and all, you can see later on, and Mars also. And some of the research areas in last slide in image processing are image morphing, image inpainting, video analysis, virtual and augmented reality, current topics, image super resolution or multi-resolution techniques, computer vision, biomedical imaging, statistical techniques to account the uncertainties, stochastic models. So I think these are the only slides which it ends. In fact, thank you very much for your attention. This closes my talk, in fact, briefly, but I could not spend too much of time. Okay, given to you now, sir.
Yeah. Now we can stop sharing. No?
Yeah, now you can remove.
Yeah. Yeah. Thank you, sir. I thank Gopal Krishna, sir, for giving me wonderful insights about the trends in satellite image processing and other details about the ISRO, including ISRO response programs. I hope the participants may get a lot of insights, and they will try to apply for ISRO response programs. I am very much thankful, sir, for delivering a wonderful session for about 1.5 hours. Okay. Now we are taking.
No, in fact, we could not spend too much of time. In between, some time is lost.
Yes. So now I request participants, 1 or 2 participants, you can interact with the Professor Gopal Krishna, sir, for any queries. Then we can wind up the session.
Hello, sir.
Yeah.
Good evening, sir. This is Leelavati, sir.
Good evening.
I would like to know what is the scope of research in the satellite image processing, sir?
No, I gave you a lot of topics. There is a lot of scope. Everywhere there is a research in satellite image processing. Satellite image
Using
processing.
MATLAB,
Yeah.
sir, is it better to develop, proceed using MATLAB or machine learning, sir?
Yes, sir. Today you have so many libraries available. So those libraries you can use it to develop even the satellite image domain also. There is open tools are available which you can use it and make your own tool and then generate.
Okay. Okay, sir. Thank you.
Okay.
Any more?
Good evening, sir. So this is Mohammad Imaduddin. It's been pleasure to attend your session today, sir. Sir, I just wanted to know, you spoke about image fusion and various techniques. Which technique is the best among? Is PCA the best among all the techniques you displayed?
No. It's a for certain application or our applications, at least satellite applications, wavelet based is the best which I have shown you lastly example. See, we have studied so many. PCA also is good, but in certain cases some patches will come. So in the wavelet based, you can tune it better. That is what our experience showed.
Thank you, sir. Thank you very much.
Okay.
Any more participants can interact?
Good evening, sir. This is Dr. VNA.
Yeah.
As part of Department of Mathematics, what type of mathematics you are using in this, sir? I think I got the message about MATLAB. Apart from this, is there anything, sir?
No. In fact, ISRO, we don't use MATLAB or something. We develop our own programs. What I'm telling is, today there are so many libraries available, even using MATLAB. Certain things like correlation, convolution and all, MATLAB is the best one, like image matching when I told. So in that, the correlation is the important aspect. Our feature detection is the important aspect. Covariance and then single value decomposition, then least square estimates. These are all used from the MATLAB if you wanted to do so. Otherwise, usually we use for the basic mathematical things for the MATLAB, but otherwise we develop our own programs in ISRO.
Okay, sir. Thank you so much.
Okay.
Yeah, I think. Yeah, once again, I thank Professor Gopalakrishna Garu for giving a wonderful session. And with this, we would like to conclude. Now, I thank all the participants for listening patiently the lecture and other inaugural session speakers. Let us meet tomorrow at the same time at 7 o'clock. I think my convener will send you a link. Rasool, is the same link or do we send another link?
No, sir, we'll send another link.
Yeah, we will send another link tomorrow. Please join. Okay. Tomorrow also we have wonderful speaker from IIT Bombay. I think he is a friend of BJK sir. Yeah, Professor Krishna Mohan. He is also talking on the satellite image processing. Okay. Thank you one and all for joining once again. Please don't miss this session.
Okay, sir. Good night.
Yeah.
Thank you, sir.
Thank you all. Thank you all.
Good night.
Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.